everyone. Hi everyone. I'm Changwan, a postdoc working with Professor Saman Amrasinghe. He suddenly couldn't attend, so I'm going to present our work, compiler support for structured data. Can you hear well? So in 1957, yeah, and quiet. Sure. In 1957, Fortran already introduced array programming, or the arrays can be vector like matrices or high dimensional tensors, but they are always dense. However, real world data is mostly structured, like for instance, many tensors and graphs are sparse. And as you can see this video, many values are replicated and some data is symmetric. So in this talk, I'm going to propose several approaches to address some issues posed by some structured sparse data. So I'm going to talk about how to unify the concept of sparsity and lossless compression. And I'm going to propose a loop depth or language to iterate the structured data. And I'm going to talk about two autoscalabilities. So here is a simple 2D array with a bunch of zeros. So we can store this in compressed sparse row CSR format. So as you can see, zero values are implicit, so filtered out. Actually, they are more one values than zero values. So we can filter out one values. So as you can see, we introduce a field value array, which is one. So we can see the size of the format is reduced. If you look at even closely, we can recognize, as you can see, this array, the same values are repeated. So we can actually store same values in a group. Then we can retrieve this array by only tracing index of the first entry in each group with corresponding field values. Okay. So this is actually long length encoding RLE format. So you can see the size is significantly reduced. So we actually implemented this concept and incorporated this into a sparse tensor algebra compiler. And here are some experimental results. So RLE is shown to be effective to reduce the size of the communication cost as well as the storage requirement. But actually RLE is usually expanded when it's computed. But we directly compute this RLE data structure without expansion, so we can also achieve good performance improvement. Now I'm going to talk about a looplet or language to iterate structured data. So actually there are many expressions, but complexity also comes from the same expression with different data formats. Like these two data, like you can see the formats are different. So here is a simple example of the product of two vectors, C is AB. If both arrays are dense, it's trivial, right? So we can just increment pointer one by one to traverse in this way. If the one array here A is sparse, we can still iterate. Like we can actually iterate non-zero values in A, and we can gather non-zero values in this way. If both arrays are sparse, we can use a two-finger merge strategy like this. So we can still generate like whether each array is dense or sparse. This is an interesting example. As you can see, P is composed of the one dense block, but the other entries are zero, right? So we can still use a two-finger merge strategy like this. But actually, we can do this more efficiently because this is dot product, like intersection operation, not union operation. So we just need to traverse a fourth entry to seventh entry of the array A, right? So we can use binary search for more efficient search. So we showed how to generate some dot product when each array is dense or sparse. But actually, there are many different data structures for each array. And Taco, a sparse tensor algebra compiler, can generate those four cases for arbitrary like equations. And Halide also efficiently generate code if the one array is like a sparse or like some blocked or ragged array. Cora also generates some code when each array is dense or ragged array. On the other hand, looplet can generate various codes, including those cases. So looplet language is a general language to iterate over structured data using these 8 primitives. So here is an example. So this array can be iterated in this way using different combination of primitives. Here stepper is like a for loop, and pipeline is like a concatenation. And code generation for from these iteration protocols is pretty simple and mechanical. Here, iteration protocol means an infrastructure to express some data structure using these 8 primitives. Also, to co-iterate more than one array, we actually merge the individual iteration protocols. And for high performance and simpler code, we use rewrite rules here. So actually, looplet language can actually generate very sophisticated arrays, structures, or like ragged matrix, or run-length matrix, and symmetric, and so on. So now I'm going to talk about 2 auto-scheduling languages. The first one is asymptotic scheduling language, because for sparse computations, input data pattern actually affects performance. But the first one doesn't consider like input pattern, input sparsity, but the second scheduler actually considers input sparsity. So usually a domain expert for sparse computations, domain experts actually write a tensor expression. And this tensor expression goes to a tensor compiler, tensor framework, that actually includes some tensor algebra compiler like Taco, and it generates some results. But actually to achieve the best performance, a performance engineer actually uses like loop transformations. So here scheduling. But the problem is that if we wanna like embed like Taco into like scientific libraries or like SciPy or NumPy, actually it's very hard to understand the pipeline. So actually engineers are actually very hard to optimize those kernels. So what we actually want to replace this engineering effort with auto-scheduler. So this auto-scheduler doesn't consider input data, as I mentioned, and it just we just consider asymptotic time complexity. I'm going to show you. So this example shows why asymptotic time complexity is important for dense computation. So the left figure shows vector A is matrix B times matrix C times vector D. So the first case is like we actually compute BCD at once. Then you can see 3 nested loops. So the time complexity is n cube. On the other hand, we can compute CD first, and then we can B is multiplied with the intermediate results of the CD, and you can see 2 nested loops, each with depth to right. So the time complexity is reduced to order n square. And for sparse expressions, we have to consider much more. For instance, a data format also affects asymptotic time complexity. So our auto-scheduler conceptually enumerate all the schedules, all the possible schedules like this. But we efficiently prune the search space by comparing one cost to another. In this case, the second candidate includes 3 nested groups, depth is 3. So this is filtered out as I showed you, because it's asymptotically inefficient. Similarly, for like union operations, can be asymptotically worse than intersection operations because it has to traverse all the entries of the 2 arrays. So like some schedule that includes union operations, like can be like filtered out if there is a corresponding schedule that uses intersection schedule. So we actually significantly prune the search space. That's order, so we achieve the orders of magnitude speed up for this schedule. So here are some results. So these blue curves are like performance with Taco, and those red curves are performance with our auto scheduler. So as you can see, performance, we can achieve orders of magnitude speed up for random sparse matrices with different sparsities. So now I'm going to consider how I'm going to consider like another auto scheduling with input sparsity. So like the following question is, can you find the like best schedule if we know the input pattern? So as you can see, those 3 matrices, an optimal data format is dependent on the input patterns or size. So here, like we can choose like an optimal input format, and we can also, given an input format, we can choose an optimal schedule that leads to the best performance. So to do this efficiently, we developed a machine learning-based cost model to avoid actual computations. It actually takes like input sparse matrix as well as super schedule, which is composed of format plus schedule, and it outputs a predicted runtime. And due to time constraint, I'm just going to talk about how features of sparse tensors are extracted. So usually we used to extract features with human effort, but this is very inefficient. As you can see, there are so many efforts, and we don't know which features affect performance. So people actually like treat this sparse matrix as image, and we actually apply like a convolutional neural network, CNN. But if the sparse matrix is large, then we cannot apply some CNN method. So we actually can do downsampling to reduce the size of the sparse matrix. But actually, this can lose some local properties, so it can capture global properties well. For instance, suppose there are 3 by 3 like blocks in 1 billion by 1 billion sparse matrix, and after applying this downsampling, we would lose some local feature of the 3 by 3 like blocks. So what we did is we actually applied a sub-manifold sparse convolutional networks. So we start from the original sparse matrix, and we gradually reduce the size of the sparse matrix, and we apply convolution for each step. So we can capture like both local features as well as global features. So here are some results for important kernels. So actually achieving 5% performance improvement over MKL is known to be hard, but for given some like input formats, like if the non-zeros are clustered well, then actually we can actually achieve over 2x performance figure. Okay, thanks.
Thanks. So I just wanted to make sure I understood correctly. So this I guess DSL that you're proposing, if I have, say, data that is in, a CSR format, and I have a dense matrix that is, column major format, given that input format, can it operate directly on that, or does it have to reorganize the data before?
We have to reorganize it.
I see. And follow up, is there any, planned support in case I don't want to reorganize, or is the reorganization not the bottleneck ever?
So actually, Taco supports like if given a format, Taco actually transforms some format to another.
I see.
And there is another work at PLDI 21. It actually shows how to automatically convert one format to the other. So we can actually efficiently convert those formats.
I see. Okay.
Is this at the point where I can start playing with it in my own workflows, and if so, how?
Can you say again?
This DSL, the compiler for it and so forth, is this at the point where I can start integrating it into my own workflows? And if so, how do I do that?
Oh, that's a good question. Like, I think, suppose we restrict, we restrict to a bunch of sparse tensor algebra kernels, then you first identify like some Einsums equations. Once you identify, you can just put each of Einsums equations to the compiler. Then compiler can generate some efficient code. But there are some other issues because there could be some optimizations across Einsums notations, right? So we have not supported these optimizations, but I think in most of the cases, real cases, a few Einsums notations like dominate the performance. So I think cross optimization may not work, except like some cases where like iterations will work.
Yes, sir. So, thank you. First of all, I'd like to thank the organizer for inviting me here. It's good to be here among so many of the well-known, researchers in the Tensor community. The work I'm about to present is a collaboration between the University of Oregon, Intel Labs, LPS, and Sandia National Laboratory. And I'll be talking about linearized tensor formats for performance portable tensor, sparse tensor computation. The one thing I'm going to do, I'm actually here to sell everyone on the idea that when it comes to sparse tensor formats, everybody's been doing it wrong, and we have found the right way to do it. And that going forward, everybody should use our format. That's what I want to do here and convince people of that fact. It's a fact. So a fundamental problem in sparse tensor computation is how to store, group, and organize data, the sparse data. And the objective of that is so that we can reduce tensor storage so that we load them faster and do the computation faster. And to improve data locality so that we access the data from the fast memory as much as possible, which again reduces the computational time. And to increase parallelism because modern multi-core systems have so many compute units that you want to be able to fully utilize them. And lastly, to decrease workload imbalance and synchronization overhead so that you don't have as many threads wasting its time during the computation in parallel. The problem is many of these goals are conflicting. So if you improve one, you oftentimes you end up with a decrease in performance in the other aspects. So what is the state of the art? The state-of-the-art sparse tensor formats can be classified as one of the three: list-based, tree-based, or block-based formats. A primary example of a list-based format is, of course, the well-known CO, the coordinate format, where you basically simply list the non-zero elements with the non-zero value attached to a tuple of the index values. For a 3D tensor like this, we have the IJK or mode 1, 2, and 3 indices and the non-zero value. The problem with this is that while it's simple, the non-zero elements can be arranged in any arbitrary order, which means that you have poor data locality, and every update has to be done synchronously using an atomic operation, which can be very expensive with many threads. For example, probably the most popular tree-based format for tensors is the CSF or compressed sparse fiber, where you represent a tensor as a group of subtrees. So each subtree is made of n levels. So you have, in this example, mode 1 or I indexed as the root, then the mode 2 or J on the second level, and mode K, 3 or K on the bottom. And each subtree represents a unique index for that mode. So here we have 4 subtrees because you have 4 unique indexes for I. The advantage of this format is that you can compress the data by sharing common indices. So for example, for the first 2 non-zero elements, you have 1, 1, 1, and 1, 1, 2 as the indices. So in the top left corner, you have 1 and 1, the blue and the green one, shared among the 2 non-zero elements with the K values of 1 and 2. So this allows you to compress the data. And also, if you assign 1 thread for each of these subtrees and you're computing for mode 1, then each of these subtrees can compute independently without any communication with each other because each subtree represents all the non-zero elements that updates a particular index in mode 1. The problem with this is that, of course, if you're targeting the different modes, say you're doing mode 2, MTTKRP, then you need to rearrange this subtree. So what happens is that more often than not, you have n copies of the tensor, where n is the number of dimensions of the tensor, so that you're optimizing for every mode, which can, of course, be very expensive. An example of a block-based format is haiku or hierarchical COO. Basically, you subdivide a tensor into smaller subtensors. And basically, if you have a smaller subtensors, you need fewer bits to represent the indices. So you achieve compression by reducing the number of bits required to store the indices. So in this example, we have a 2 by 2 by 2 subtensor highlighted in yellow, and it has 3 non-zero elements. So the first block represents the first subtensor block, and then you can reduce just ones and zeros to represent the indices. The problem with this is that sparse tensors are extremely sparse, so you have trouble finding dense blocks to represent. So sometimes you can actually end up using more data to represent the indices and even the CO format because it's so sparse. So if you summarize these formats, you can see that they do well on some aspects of these properties like mode orientation or copies, data locality, parallelism, and load balance, but it's not perfect on every one of them, and for the reasons that is described. So why is that? Why are tree and block-based formats popular with the current research HPC community? And my guess is that it's because we're coming from decades of research in sparse matrices, and this is what's been popular with sparse matrices. So naturally, we extend these formats. For example, CSF is a high-order extension of CSR. So we've had this preconceived notion that these type of compression is good for sparse matrices, so therefore they must be good for sparse tensors. However, because of 2 properties of tensors, these are actually not a good idea. The first being that tensor computation often operates over every dimension. So if you compress the data along one mode, it's good for that mode. And for matrices, it's either the whole computation or half the computation. And so for compression, it kind of makes sense because you're getting a good benefit from the compression. But when you have a tensor, you compress for one mode, that means that you're suffering on the other modes. And with the number of dimensions going up, that kind of gives you a dimension return in the benefit of compressing along one mode. So that's why CSF is usually not a good idea. Because of the dimensionality, the number of non-zeros are few and far apart, and so they're extremely sparse. So for you to find dense subblocks in a sparse tensor, that's a much more challenging problem than in a sparse matrix, even if you do some kind of permutation or random redistribution. For example, if you take the sparse tensor from the Frost repository, you get a sparsity that ranges from 10 to the power -2 as low as 10 to the power -15. So they're extremely sparse. So formats like Haiku have a lot of problem either by tuning the blocks to find dense subblocks and to create the subtensor from the from the original tensor. So our hypothesis was that simple mode agnostic and list-based formats are actually best suited for sparse tensors. And I will have to give thanks to Tammy Kolda for setting me on this path, because I think she's always been pushing this idea that, you know, these kind of compression is not good for sparse tensors. But we still have this challenge of how do we improve data locality and reduce conflicts, because we saw with the COO format that these were challenges. And additionally, we also want to make him simple and performance portable, because now we have a wide range of architecture that we have to kind of, you know, design our algorithms for, because, you know, Moore's law come to an end. So now we're designing specialized architectures left and right. So our research, we yielded two different formats, ALTO and BLCO, or adaptive linearized tensor order and block linear coordinate for CPUs and GPUs respectively. And BLCO is just a small variation of ALTO. So in fact, we really have a very similar format that's suited for both architectures. And we apply this linearized formats to streaming tensor decomposition, on-the-fly Cattaro product for CP-APR, and non-negative sparse tensor factorization for GPUs implemented in Planck. Some of these are ongoing, so I won't cover them, but we'll talk about ALTO and BLCO in greater detail. Any questions so far? Hopefully I'm not going too fast. I have a tendency to speak really quickly when I'm nervous. I am nervous. It's my first talk in over a year. Anyway, so let's look at an example of how ALTO is generated. So we basically take the index values and you take the bits and you interleave them, grouping them by the same position. So here we have the bit mask on the top right. So they're grouped by 1 bit, 2 bit, and 3 bits, which is hidden by the message here. But the group of 3 bit is basically the 0 bits from each of the indices. So K0, I0, and J0. And then we have 2 bits because it's a 4 by 8 by 2 tensor. You need 2 bits for I and J, but only 1 bit for K. So the second group is bit 1 from the I and J indices. And then since there's no third bit except for the J index, you have 1 bit for the bit 2 of the J index. And within each bit group, we basically order from the longest mode to the smallest mode. So within the 3-bit group, you have J and then I and then K. So this is somewhat similar to the Morton Z or the Z-curve ordering, right? You're interleaving the bits. But we're different from that, as we'll cover in more detail later, that we don't have to have the same number of bits for each mode. We're adapting to the size, the irregular size of the tensor bits. So basically, if you convert those bit interleaving into a new integer, you end up with a new integer that ranges from 0 to 64, or 63, because it's a 4 by 8 by 2. You have 64 unique elements in the tensor. And so we basically map each of these non-zero elements to a single index in this line of from 0 to 63. Now, the advantage of this format is that it's a list-based format. So dividing the work or partitioning the work among threads is fairly simple. You just have to divide it by the number of threads you have. And then you have these line segment partitions, as you can see on the right. The one unique thing about the linearization is that when you divide the partitions, you don't end up with the same subtensors. As you can see from these two, each one has a different shape. Another unique property is that they can actually overlap. So until now, most of the decomposition of the tensor space was done into usually regular sized, identical sized, non-overlapping. But our format doesn't care about that. It can do overlapping subtensors. And the advantage of that is less restrictive, so it's easier to load balance. So encoding the decoding the bits is fairly simple. You have bit level gather and scatter, and that's actually cheap to do on CPUs. And so if you look at let's say the MTTKRP algorithm, at the high level, you divide the workload into partitions. So for Haiku and CSF, these are Haiku blocks or CS subtrees. And then you iterate over the non-zero elements in each partition. And then you fetch the indices and the non-zero value. You load the appropriate rows from the factor matrices, do the MTT-KRP computation, and then you update the row IX for if this is a mode 1 MTT-KRP. For Ku and Haiku, you have to update atomically because there's no guarantee that you're not working on the same row as somebody else. Whereas you can update freely without a synchronization with CSF. But remember, with CSF, you have to have n copies of the tensor if you wanted to do it with synchronization free. So that can be very expensive in terms of storage. Now, if you do this using the auto format, what you have is basically each of these parallel partitions are auto segments. And then you fetch the auto index. So now you only fetch one index versus 3 or n for n-dimensional tensors. And then you have to go through a decoding process. Now, the decoding can be done actually very cheaply on x86 CPU using parallel bit extract and deposit instructions, which are very low latency and very high throughput instruction. So you basically don't actually have to pay for the decode. You can actually interleave the decode stage with loading the data for other threads. So you can actually hide the data decoding phase within the data access phase. So you can actually do this without any additional cost, more or less. You are doing it, except that you're hiding with the data access cost. So you're hiding the cost very effectively. And then when you're doing the updates, you can do this adaptively. So if the rows have a lot of reuse, meaning that there's a lot of non-zero elements per row, then you can use this using an adaptive method where you use scratchpad, you update, and then you do a global synchronization. If the reuse is low, then we can actually use atomics. And this allows you to do the synchronization much more cheaply than using purely atomics or using purely scratchpad-based reduction. And we can do the reduction more effectively by looking at the boundaries overlap between the different partitions. And that tells you which partition you need to look at when you're doing the synchronization at the end, when you're doing the reduction. So you don't have to do reduction blindly. You can do it more effectively by looking at the bits and getting the boundary information from each partition. One thing that I do want to go is that it is different from Z curve because we can actually adapt to irregularly shaped tensors, and which further reduces storage, which further reduces the cost of doing the encoding and decoding. So that's where we kind of differ with the Z curve. So we have kind of satisfied all the different properties. And so we can kind of hit the sweet spots on every specific property that we're optimizing for. And then if we do a comparison against state-of-the-art, and so here we're comparing it against an Oracle selected best format from the mode agnostic group, which are Ku and Haiku, and for the most specific format, which are from CSF and CSF with cache blocking. And so on the left block, we're comparing the speed up, which is basically saying that the slowest one is the mode agnostic format, the best one selected for 415 and taking the geometric mean speed up. And that's a baseline one. And if you take the most specific format with n copies, you can get a 4.7x speed up. By using auto, which only keeps one copy in a list-based format, we can get an 8x speed up. And if you specialize a code to target a specific rank, in this case, rank 16, we can get an even higher speed up. In terms of compression, we compare against the worst, which is the CSF with n copies. If you use mode agnostic Haiku, you get a 2.9x compression. And using auto, you get a 4.3x compression in the data. So we're actually doing fairly well in both the performance and compression. Let me see how I'm doing at time. I'm almost done. So I won't be able to go through this in detail, but we're doing much better than the competitor. That's all that matters, honestly. And the cost of doing the conversion to generate the auto is actually cheaper than CSF or Haiku by quite a bit. So the GPU. So what do we need to do to kind of jump through the gist of it? The GPU does not have a parallel bit extract deposit instruction, right? So you can't actually do that because that becomes extremely expensive and you can't hide that cost among the data load anymore. The number of threads is much higher, so updates are much more expensive, and GPU have limited on-chip memory. So a lot of these tensors will not actually run on the state-of-the-art libraries like Reddit, Amazon, and I think NIPS, because they just don't fit into GPU memory. So what we did was we just take auto, and instead of interleaving the bits, we just concatenate the bits. So we still have them auto ordering. Oh, I don't have an example, but we still have the auto ordering, but we just interleave the bits, de-interleave the bits so that bits from the same index are consecutive. So now we can basically use the GPU's shift and mask to extract the indices, and then everything else is the same. We can also cut off the bits that are above 64 and use them as block indices. And then you can take those blocks and stream them into GPUs one at a time so that we can actually process tensor that are too big to fit into GPU memory. And then we have a sort of an adaptive hierarchical way of synchronization that basically stores data in register, shared memory, and global memory as necessary to further reduce the cost of synchronization, because with so many threads on GPUs, it's actually more expensive to do synchronization over global memory than on a CPU where you only have dozens of threads versus tens of thousands of threads. So overall, we can actually achieve 2.6 and 2.12x speed up over MMCSF, which is a GPU variant of the CSF format on the V100 and the A100. And we can actually get 2.25 and an unspecified Intel device because they won't let me talk about it. But you can probably guess which GPU that they're talking about. But across any GPU that we can get a speed up using the BLCO format, which is a very simple addition to the Alto format. So the gray and the yellow bars are Alto format cost generation. And the red and the blue are the additional costs you have to do to go from Alto to BLCO. So it's a very small overhead. And then it is much more cheaper to generate. And it actually runs on these Amazon Patents and Redis tensor just as effectively as the other smaller tensors. And one of the biggest benefits is that we get consistent performance in GPU across any mode. With CSF, you get variance in performance because of the way that you compress the data. But since you are keeping everything as a list, we can actually get consistent high bandwidth, 80% of the peak bandwidth of the system on all the kernels across all the modes, whereas you get huge variances on compressed formats like CSF. So going on a future architectures on GPUs, we're less sensitive to variations in number of threads and synchronization costs. We're just because we're keeping the data in a much simpler format. And I think that's it. Thank you. So the GPU, the format for GPU is called BLCO, but it's basically just a rearrangement of the bits from the Alto format. So it's basically the same format, just made easier to extract bits on a GPU because GPUs don't provide these parallel bit extraction operations, while CPUs provide this natively.
How about the other accelerators, like let's say some AI accelerators or something? Those not specific to
we
GPU?
haven't tested on an AI. I have access to the Cerebra system, but I expect that they're really good for dense computation and not sparse. So that's sort of on our to-do list. We haven't really explored any other accelerators because GPUs are kind of the most popular one available at the moment.
Thank you.
But we did test an Intel device without a name. Yes.
On the CPU, does it matter about the bit interleaving versus blocking to either work?
So we're actually moving towards the BLCO type format because while they do have this in both AMD and Intel CPUs, these parallel bit scatter gather operations, because the overhead of creating BLCO is so cheap compared to the original cost of Alto, we're moving towards just doing bit gathering and then doing shift and mask to extract the bits. So Alto works on almost every x86 and AMD CPU. I'm not sure about ARM CPUs, but BLCO is a very good alternative, sort of an evolution of Alto, because it's the same data reuse and same parallelism, but a much cheaper encoding and decoding cost. So, well, comparable encoding and decoding costs. So going forward, we'll probably use BLCO on the CPU, and it doesn't really matter because it's very easy to go from one to the other. Thank you. Hopefully, I've convinced everybody to use Alto from now on.
Hi, everyone. I'm Talua, and I've recently been working with John Owens and Joel Emmer on leveraging the stuff we heard in the prior two talks for graph algorithms. Okay, so graph represents relationships between entities. These graphs may include things like circuit simulation data, social communities, or road networks. For this talk, I'll be using the graph distance problem as our example graph problem. The goal is to find the minimum number of hops, or the depth at which each vertex is reachable from a set of starting vertices. So if we suppose we have a social network such as Facebook, in this case, the graph distance problem seeks to answer a question like, how many connections away is each person from a particular friend? So if we start off with this friend, we'll search for friends 1 hop away, then 2 hops away, until the entire graph structure has been explored. And this problem is often solved in a breadth first search manner. But overall, given a graph problem such as the graph distance problem, an implementation has many things to consider, including the general approach or algorithm for solving the problem, synchronization considerations, which graph view to use, the data structures for the graphs and other data types in the problem, partitioning, load balancing, and finally, how all of these interact together with the architecture on which the implementation will be executed. The point is, this is a large combinatorial space of things to consider. In trying to attack this complex problem space, implementations tend to intertwine these concerns of the problem they're trying to solve with how they solve it. There's no separation of concerns. Implementations are described in natural language and pseudocode, which is often imprecise. It's difficult to compare how they're different, and it's difficult to methodically explore the implementation space. With this in mind, our work focuses on extending tensor algebra notation, or Einsums, to represent graph algorithms. Our hope is that this will provide a precise, elegant, and expressive abstraction to express graph algorithms and their implementations. And we want to leverage this abstraction to enable methodically exploring the algorithm and implementation space. And finally, to provide a bridge between graph algorithm developers and the tensor algebra compiler community, so leveraging work of folks in this room. So with that in mind, let's look at how the tensor algebra compiler community approaches problems. This is mentioned by one of our speakers today, but a lot of it stems from Halide, where they had this concept of separating the algorithm from the schedule. And in Halide, this enabled a systematic search of the scheduling space while keeping the same algorithmic approach. Since then, the tensor algebra compiler community has expanded on this design philosophy and run with it. As an example, one work on the hardware side is Teal, which Nandika Nayak will be presenting later today. That is essentially a compiler and tool that enables a user to model and compare sparse tensor algebra accelerators in an apples to apples manner. And Taco, which we've seen in 2 talks before mine, is also a tensor algebra compiler, but it generates CPU and GPU code. And there are many other works in this area that use this design philosophy of a separation of concerns. So in nearly all cases, the first concern is describing what is the computation. And this is done using variants of tensor index notation, or Einsums. In our case, our operational definition of an Einsum is that it is an algebraic expression that indicates a set of multidimensional input and output tensors. And it creates an iteration space, which is the Cartesian product of all the indices or ranks in the expression. And finally, at each point in that space, some computation is being performed. The next concern is, how does this computation happen in space and time? So how do we actually walk the iteration space? And this is where things like iteration and loop order, tiling, parallelism come into play. And finally, another concern is how the data is represented. And all of this with the computation, the mapping, and the data specs bind together for actual hardware or platform-specific implementation. So by doing this, both Teal and Taco are able to succinctly characterize and model different tensor algebra implementations on hardware and or on software. And part of what makes this work a success is they've done a great job of abstracting each level and providing a clean interface between each of them. So going back to the graph world, attacking this combinatorial problem is hard. If we can divide this space into manageable parts in the way tensor algebra tools do, we can then solve smaller and easier pieces of the problem separately. the problem becomes tractable. And so that's what my work is trying to do, is to adopt a similar design philosophy of a separation of concerns by leveraging tensor algebra tools. So rather than using imprecise language, we can now use Einsums plus a set of specifications to specify a given implementation. However, the current tensor algebra framework space is not enough, as graph problems face challenges not currently addressed by traditional tensor algebra. Thus, we need to extend Einsums. The first challenge is that several graph problems tend to differentiate between the vertex and edge entities of the graph itself and the properties or features of those entities. For example, you might have edge weights associated with edges, or certain values associated with the vertices themselves, or you may even be working with something like a Sparse property graph. So to differentiate between vertices and edges and their features, we extend the notation to explicitly separate out computation on the coordinates of an iteration space, which we call merge operators, from operators on tensor values. Let's walk through a simple example with breadth first search. So given this graph, we can represent it as a 2D tensor of its adjacency matrix. Without even looking at the tensor values, we can already start mapping things to the graph world. So the S coordinates map to vertex entities that have destinations. The D coordinates map to vertex entities that have sources. And the SD coordinate tuples map to edge entities. And breadth first search also has a frontier, which initially contains our starting set of vertices, in this case 0 and 2. And we can represent this by this 1D vector in the Einsum world. And then also records the depths of each of the nodes and whether or not they've been visited yet. So the first step in BFS is to gather the neighbors of all vertices in the frontier. Without even looking at the values of our two tensors, we can see that this is an intersection of the S, or source coordinates, in both G and F. Our extended Einsum notation explicitly denotes this intersection as a merge operator on S, parameterized as follows. Now, breadth first search also needs to update the depths at which each neighbor is found. This requires looking into the current depths of the frontier and the edge weight, which is 1. And for each of the gathered neighbors, we add their edge value to the current depth of their source vertex in the frontier. In our extended notation, we apply addition as our compute operator. And this gives us a temporary result where for each source that was in the frontier, in this case, vertices 0 and 2, we have a temporary depth value for each of its neighbors. And next, we need to make sure there's only one of each neighbor across all the sources. So this requires a reduction across the S rank, or the S dimension. And again, we can describe this as a union of all the S coordinates, with the compute operator being a min operator. So many of you may recognize these steps as matrix vector multiplication in a traditional Einsum. However, in a native graph view, vertices and edges really are separate entities from their attributes or properties, and linear algebra representations tend to conflate this. Our extension benefits from having a richer set of operations where we can do separate things to vertices or edges and their attributes. And then we can look at which coordinates do or don't exist in the involved tensors and use that to filter values we end up looking at within a tensor, if any of them. And then there's one last step in breadth first search where we need to filter the new frontier based on what has been visited, and we can do that with take left merge operator. Okay, so another characteristic of graph problems is they tend to contain complex dependencies and are iterative or recursive, with computation stages that build on previous stages. So for breadth first search, for example, we continually update our frontier and the set of visited nodes until we've traversed the entire graph. Traditional Einsums can't handle this in 2 ways. First, Einsums will employ an update procedure that is analogous to static single assignment, where input tensors cannot appear in the output. And yet here, as you can see, our frontier is changing over time. And then secondly, if this is a single step of breadth first search, there's no way to express that this is happening multiple times unless we rewrite the Einsums for each of these steps over and over again. So to support iteration, we extend Einsums by adding a generational dimension, which we denote by I. And this new rank indicates a data structure is changing over time and that the Einsum expressions should repeat until a stopping condition, indicated by this last expression here, is met. So now we can express iterative updates and iterative steps. And the nice thing about using this Einsum framework is that adding a generational rank is already part of the tensor machinery. It's simply a new dimension. Third, graphs require computations beyond standard mathematical ones, in particular things like conditionals, such as this if-else block in this snippet from connected components. To support conditionals, we allow expressions in the indices of an Einsum that filter the iteration space. And secondly, traditional tensors tend to update an entire output tensor all at once. But in the graph algorithm world, they tend to contain selective updates to data structures. Thus, we add a populate operator that enables piecemeal or partial updates of output tensors. And finally, a common characteristic of graph algorithms is that for a given graph algorithm, multiple variations exist. So let's go back to BFS. The variant we just walked through earlier is known as top-down or push BFS, where sources in the frontier check for their neighbors and push updates to their neighbors. It turns out there's another way to look at this problem, which is bottom-up or pull BFS, where on each iteration, destinations check if any of their parents are in the frontier. Now, it took decades till 2012 before this pull BFS approach was discovered by Scott Beamer. And it turns out that in practice, this approach is often combined with the push approach in high performant BFS implementation. So this is an important variation. So in our framework, to be able to handle things like this, we formalize this concept of having variance by adding another concern to our separation of concerns. Namely that an Einsum can have algebraic variance derived by employing algebraic manipulations to an Einsum. So for push BFS, if this is the specification, we can now apply this set of algebraic transformations to get pull BFS in 4 simple steps. This concept of algebraically modifying the Einsum is powerful as it allows us to come up with other graph algorithm variations. Thus, overall, while we employ a similar separation of concerns as tensor algebra, we needed to extend the notion of an Einsum to handle the characteristics of graph problems, including differentiating between the vertices and their properties, handling iterative steps and dependencies, handling partial updates and conditional computation, and enabling simple algebraic modifications of an Einsum to express alternative algorithms. So now, rather than our imprecise language, we can now use Einsums and that set of specifications to describe a given implementation. So given this framework, what can we do with this? Well, for one, we're able to express a wide range of different graph algorithms. I'm showing a small sample here using our shorthand notation. Secondly, extended Einsum specifications map directly to native graph world implementations. So more specifically, if I have this full breadth first search Einsum specification with the Einsum and the mapping specs, I can manually right now compile this to an implementation within a highly performant graph GPU library like Gunrock. So our additions that we've made to Einsums now makes all the work that the tensor algebra compiler community has done accessible to native graph implementations. And finally, we can extended Einsums enable us to do systematic exploration. And Changwan talked about this in his talk, where you can explore different mappings. And in our case, we also want to explore different algebraic manipulations. You can explore different data formats and explore different platform-specific optimizations. And in fact, we manually explored the space for best-first search and came up with 26 different VFS variations, some of which are beyond the traditional push-pull VFS. And these variations were hand-compiled to generate Gunrock GPU code, and some of them gave a speed up of over 2x compared to the traditional baseline implementation. My current work is looking at, so all the things I mentioned before were done manually. So right now we're looking at how can we do this automatically? And then also, how can we leverage prior tensor algebra tools? So Nandika is going to talk about TEAL later on today, but we're looking at how to extend that to support graph algorithms for graph accelerators, and also to extend it to target GPU backends and frameworks like generating Gunrock code. And finally, we're looking into how to formalize the space of algebraic manipulations. All right, thank you. Grateful for all the people who gave us feedback and discussions, as well as the Microsoft Research Program for funding. Thanks for listening.
So do you envisage a world where I can specify a graph algorithm as an extended Einsum, and then on the back end, and I plug that into a computer and it does an automated search and says, okay, I ran through 10,000 variants of your algorithm and the best one is this.
Yeah, that's exactly what we're trying to get to, the big picture goal. Yeah.